Okay, so we're going to continue on with connecting our understanding of electric potential and electric field by looking in this video at sources of electric potential and looking at conductors in electrostatic equilibrium. We're going to start with a real brief summary and then move forward. So let's just jump into it. So let's start by summarizing briefly what we've discovered about the connection between electric fields and electric potential. This picture here illustrates this summary. There's three important bits of information that we have about electric fields and electric potential. First, the electric field is perpendicular to equipotential surfaces. Second, the electric field points in the direction of decreasing electric potential. Sometimes this is called downhill. Third, the strength of the electric field is inversely proportional to the spacing between equipotential surfaces. When the spacing is smaller, the electric field is larger. When the spacing is larger, the electric field is smaller. We can use this information to combine electric field and electric potential pictorially to visualize what we know. The first picture here shows the field and potential around a positive point charge. For a negative charge, the electric field would point in the opposite direction. The second picture shows the field and potential lines for what's called an electric dipole, which is just two unlike charges that have some separation between them. And then the third picture depicts the field and potential for a uniform electric field and uses a parallel plate capacitor as an example. So from here, we're going to look at a couple of sources of electric potential. We're going to explain how we measure electric potential and compare the electric potential and electric field in a conductor that's in electrostatic equilibrium. Now, more than likely, you have at some point in your life experienced a shock when you've touched a doorknob after shuffling your feet across a carpet on a dry day. Friction between the carpet and your feet causes a separation of charge, transferring electrons from one object to the other. In the process, a potential difference is established between the two objects. The potential difference between you and a doorknob can be many tens of thousands of volts, enough to create a spark as the excess charge on your body moves from higher potential to lower potential. The main lesson is that we can create a potential difference by creating a charge separation. A Van de Graaff generator, such as this one here, is a mechanical charge separator. It's essentially a fancy foot shuffler. The way one works is a moving plastic or leather belt is charged. Then the charge is mechanically transported through that conveyor belt to the spherical electrode at the top of the insulating column. The belt is charged by a positively charged sharp needle that ionizes the air around it. Positive charges in the air pushed away from the needle and onto the belt. Charge is mechanically transported from the negative side to the positive side. This charge separation creates and then sustains a potential difference between the spherical electrode and its surroundings. The electric field of the spherical electrode exerts a downward force on the positive charges moving up the belt. So what happens is work has to be done to lift those positive charges. The work is done by the electric motor that runs the belt. Now, the Van de Graaff generator, like the one we have in the lab, creates a potential difference of several 100,000 volts between the upper sphere and its surroundings. The maximum potential is reached when the electric field near the sphere becomes large enough to strip electrons off of air molecules, making the air itself conducting. This produces a spark and temporarily discharges that sphere. So sparks from a really large Van de Graaff generator can be used to simulate lightning for testing aircraft and power transmission equipment. For us, though, the Van de Graaff generator is important because it shows that a potential difference can be created and sustained by a device that separates charge. Lightning is the result of a charge separation that occurs in clouds. As small ice particles in the clouds collide, charging occurs by frictional rubbing, just as when you scuff your shoes across a carpet. The details are still really not well understood about lightning, but heavier particles gain a negative charge while lighter particles become positive. Natural convection processes separate those particles, and with the lighter ones being lifted toward the top of a cloud while the heavier ones fall toward the bottom. So the top of the cloud becomes positively charged and the bottom negatively charged. This natural charge separation creates a huge potential difference, as much as like 100 million volts between the top and bottom of the cloud. Lightning within the cloud, which is really the most common type, occurs when this potential difference is so great that the air molecules are torn apart, creating a conducting pathway for the huge rush of charge from top to bottom that we see as lightning. Cloud to ground lightning is also a result of charge separation. There, the negative charge in the bottom of the cloud causes a positive charge to accumulate in the ground below. A lightning strike occurs when the potential difference becomes too large for the air to sustain. Now, charge separation, and as a result potential differences, can also be created by chemical processes. A common and important means of creating a fixed potential difference is a battery, which we'll discuss in depth in Unit 5C. But all batteries use chemical reactions to create an internal charge separation. This separation proceeds until a characteristic potential difference, usually about 1.5 volts for your standard battery like these over here, appears between the two terminals of the battery. Different kinds of batteries maintain different potential differences between their terminals. Now, measuring electric potential, a variety of devices, is done with what's called a voltmeter, which is the basic instrument for measuring potential differences. So the probes on the voltmeter, these, are connected to 2 points between which there is a potential difference to be measured. We'll talk more about voltmeters, or sometimes they're called multimeters, in Unit 5C when we're talking about circuits. From here, let's move on and talk about conductors in electrostatic equilibrium. Now, in Unit 5A, we learned 4 important properties about conductors in electrostatic equilibrium. First, any excess charge is on the surface of that conductor. Second, the electric field inside the conductor is 0. The exterior electric field, then, is perpendicular to the surface of that conductor. And fourth, the field strength is largest at sharp corners. Now we can add a 5th important property, and that is that the entire conductor is at the same potential, which makes the surface of the conductor an equipotential surface. To see why this is so, this figure here shows 2 points inside a conductor connected by a line that remains entirely inside that conductor. We can find the potential difference between these 2 points by using an external force to push a charge along the line from 1 to 2 and calculating the work that is done. If we were to do that, though, the problem that we would run into is that there is no electric field in there. Okay, so since there's no electric field, there's nothing there to exert a force. So there's no force on that charge. The work then would be 0, and the potential difference would be 0. In other words, any 2 points inside a conductor in electrostatic equilibrium are at the same potential. When a conductor is in electrostatic equilibrium, the entire conductor is at the same potential. If we charge a metal electrode, the entire electrode is at a single potential. The fact that the surface is an equipotential surface and that the exterior electric field is perpendicular to the surface can now be seen as a special case of our conclusion from the preceding section that electric fields are always perpendicular to equipotentials. We can also visualize this comparison by looking at these 2 graphs here, where we see that the electric field inside the conductor. Here's a conductor here, here's the electric field, showing that the electric field is 0 inside the conductor, and the electric potential is constant throughout that conductor. Summarizing then what we know about electrostatic equilibrium in conductors is we've got this here. All the charge is on the surface of that conductor. The electric field is 0 inside that conductor. The exterior electric field is perpendicular to the surface. The electric field strength is largest at sharp corners, and the entire conductor is at the same potential. So its surface is an equipotential. So from here, we're going to begin moving toward looking at circuits by taking a look at capacitors in a little bit more depth. See you in class.